Hello, everyone. I'm Stephan Grilli, and I'd like to thank the organizers for giving me an opportunity to give you an overview of our work on Anak Krakatau. This work was done by a large group of people. I'd like to acknowledge my co-authors at the University of Delaware, and then in the UK, British Geological Survey, University College London, Birmingham, University of Southampton, Leeds, Oxford, and in Indonesia, IS Bandung, MGI Bandung, IT Bandung, and TPC Jakarta. This work was funded jointly in the US by the National Science Foundation and then in the UK by NERC. We received the funding, in fact, to study the eruption of Krakatau in 1883. This was a seminal event, one of the first events that caused a tsunami that was scientifically studied and surveyed. There is a Nature paper published in 1884 that reports on run-ups measured, run-ups over 30 meters measured in Java, and the enormous impact on Java and Sumatra, the tens of thousands of deaths and people missing. This was an event that was actually heard and felt around the world. In 1929, the son of Krakatau, Anak, emerged from the deep caldera that had been created by the collapse of the father of Krakatau in 1883. And that volcano kept growing from a very small elevation. It culminated in December 2018 to about 335 meters. But starting in June 2018, the volcano was erupting on and off. And you have a picture there from early in the day, or actually the afternoon, on December 22nd, 2018. And then a couple of hours later, the picture on the lower right shows you that the volcano was extremely active. And this was recorded from the shores of Java. Well, later that day, the volcano collapsed and caused a major tsunami that propagated in most directions and impacted most significantly the coast of Java, causing over 430 fatalities, many missing, and run-ups up to nearly 13 meters. Those run-ups were surveyed very soon in early January 2019 by Indonesian colleagues. And you can see from this initial survey that they were measured at many, many meters, 5, 6, 7 meters along the shores of Java and then Sumatra. Also, the tsunami was recorded at 4 tide gauges 2, 1 and 2 located on Java, and 3 and 4 located on Sumatra. And there again, the tsunami elevation was 7 meters, positive or negative, over the mean tide level. Also, the collapse, which turned out to be a significant volume, was measured on seismographs, and combinations of those and tsunami modeling showed that the collapse must have occurred about at 20:55 to 57 that night of December 18th. So as I said, we got funding to study Krakatau, and we're supposed to survey in August 2018, but this survey was delayed by 1 year. We ended up surveying in August 2019, but in the meantime, a collapse of Anak occurred. And immediately our team worked on assembling all the evidence from satellite video data and historical information to create a model of the rupture, and then numerical models simulating the collapse and the tsunami generation by the collapse and propagation to the far field. And those results were compared with early surveys with drones and tide gauge information that I showed you, and run-up data turned into a paper that was probably the first comprehensive paper combining data and modeling on the event. And but it didn't stop there, because we wanted to acquire actual data, and particularly submarine data. So the survey that I mentioned took place in August 2019. Data, marine geology, and sub-bottom data was acquired, and Of course, in the meantime, many other teams conducted surveys of run-ups, far-field, near-field, and a number of modeling studies that amount to about 20 papers as of now. The early evidence that the volcano had collapsed came from cloud-penetrating radar and such as the Sentinel-1A SAR. This is 2 days after the event on the right, and on the left, it's in August 2018. So the island was intact back then, and after the event, we can't see that there is a large part of the island that's missing. As I said, this had to be cloud penetrating because early on, there was lots of phreatomagmatic activity. When the magma comes in contact with water, it creates explosions, and this is the kind of scenery that took place for about 10 days after the collapse. So another picture that was cloud penetrating was from January 9th, and it showed there again a significantly large part of the island that is missing, but also if you superimpose in yellow the earlier coastline, one can see that on the north and the east, there was actually, again, an accumulation due to discharge. And that change in the island, of course, has to be accounted for in the modeling. So summarizing the initial modeling that was done, we use all that evidence and then some existing bathymetric topographic data from Giachetti et al., who had done a study in 2012 that was kind of predicting that such a scenario could occur, a major collapse, and they had actually got quite close to it. So they gave us their data, and we were able to construct a geometric model of the rupture and estimate, based on all the evidence, a volume in the range of 0.2 to 0.3 cubic kilometers. Here you can see an uncertainty on the failure plane, which leads to the uncertainty on the volume. This was discretized into our model grids, and a first set of modeling on the left NH wave, on the right fun wave, was run. The grid was fairly coarse, initially 90 meter horizontally for NH wave and 5 vertical layers, and 100 meter horizontally for fun wave. For the rheology, we considered the two that were available in NH wave, that is dense fluid, viscous, and granular material. We also considered 3 different volumes. So we ran 6 different cases and compared results to tide gauges and run-up. The agreement at tide gauges was pretty good on the arrival time and reasonable on the elevations. We have to consider also the course resolution of fun wave, and also that there were structures, harbor structures, breakwaters, seawalls affecting the tide gauge that were not modeled in the simulations. So this is probably as good as it can be considered on these factors. As far as run-up and more like inundation data, flow depths at the shore, compared to the initial survey from January, we captured all the main features that, as you can see here, along the coast of Java, in color-coded, with run-up here measured at that time up to about 9.5 meters. And the variation along the coast as a function of latitude or, longitude or latitude. And then along the coast of southern Sumatra here, the agreement is pretty good. So it meant that we had kind of captured the main features of the collapse, but certainly not exactly what happened because we had no data below sea level. So the survey from 2019 allowed obtaining all this data, but also it was combined with a better reanalysis of satellite images and historical information. Here you see some of those images, and sub-bottom surveys, multi-beam, allowed creating the debris flow. So some of those debris blocks are enormous, hundreds of meters. Some are small material. All of this was mapped and tallied, and we were able to recreate a high resolution 30-meter resolution bathymetry topography, and also estimate that the volume of slide deposit was about 0.214 plus or minus 0.036 cubic kilometers, and 45% of that was from above sea level, subaerial, and 55% was underwater. And also, the underwater slide triggered a secondary debris flow that created abrasion of the seafloor that was also estimated 2.02 cubic kilometers. So with all this data, we created new modeling scenarios with 4 different volumes, one in the low side of the range, one underlined here, which is a sort of the best guesstimate, one in the high side of the range, and then a much larger one to sort of be consistent with the earlier study. And then still considering 2 rheologies, we modeled 8 cases. Now you can see the 4 failure surfaces corresponding to the 4 volumes. We increased the resolution of NH wave to 30 meters, still using 5 horizontal layers, using our high resolution bathymetry near field, and elsewhere the bathymetry at 100 meter that we had used before. So here you can see the recreation of the digital elevation model without the water for the pre-collapse bathymetry topography on the left, and the post-collapse here on the right for one of the volume scenarios, which is the middle range scenario of 0.22 cubic kilometers. So the modeling with NH wave took place here. You can see the slide, the viscous slide in this case, flowing underwater. The parameters of the viscous slide are as follows. It's a high viscosity, so it creates a debris flow. And for the granular material, we had those parameters. Qualitatively, results are very similar for the 2 types of rheologies. And then we also increased the resolution of fan wave to 50 meter in the far field. So here is the near field simulation. Looks very similar to what we had before, except higher resolution. We can see a croissant wave that is immediately affecting the island of Krakatau here on the south, and Sertung on the north, and then there is an effect of Panjang in the back of the volcano. So we're going to look at the results a little bit more closely. And first of all, the near field generation, looking at wave gauges that are located here at 1 and then 2 in front of the volcano, we see the generation of a leading elevation wave of over 30 meters. Now, these are the 8 scenarios, and they're kind of bunched up initially. And then the wave, of course, decreases as it propagates. At the gauge 2 here, it's still 20 meters. And then later on, after propagating away from the islands, it's still upwards of 10 meters in the southwest direction. Now, in the north and east direction, waves are smaller, and that can be seen also in the tide gauge number 5 here, which is located in the north, shallower water area. We still have measurable tsunami of 5 meters there, so it will cause significant effects to the north and the east nevertheless. So in the near field, the survey from January 2019 had shown significant impact on the island of Krakatau here on the south side, Sertung on the north, and also Panjang. You can see pictures here showing the coastline cleaned of all vegetation for up to 85 meters in some situations. So very large run-ups. Those were surveyed by our team in August 2019 using a drone. So here is a drone survey line, but also other teams such as Jose Borrero here with the East Coast team. All his measurement points here represented by dots down here, and the pink line is the drone survey. And here's one of our cases with the middle of the road volume. And all the other cases, 8 cases, are bunched up here. So we can see an overall pretty good agreement between the measurements from the run-up survey or even the drone survey, except in this little corner, which is a very steep cliff here, where the modeling is probably under-resolved and H-wave is not the best model to capture that kind of fast vertical movement. But everywhere else, it looks pretty good. Another view of the same data here from the north side of Krakatau, and the run-up is plotted reversed here. We can see the measurement by Borrero et al. And the modeling, and they're well aligned. Moving north now on the island of Sertu, there were a few points of run-ups measured by the same team, and our drone survey here in the most affected corner here. Here again, we have a good agreement except in that location, which is a nearly vertical cliff. But everywhere else, we capture some of the largest run-ups. There is a gap in between in measurement, and then a significant decrease towards the end of the island here. On the back side, oh yes, this is another view of the same data. So seen from Krakatau, the picture from Borrero et al. Here shows their line of survey, which is aligned here with our simulations. And they're reported at the very tip at the end, and 11 meters that is out of the measurement here, but agrees with our modeling as well. On Panjang, on the back, we predict between 20 and 30 meter run-up. The drone survey captured a line which, in this case, it was kind of hard to figure out what was pre-existing erosion or run-up, but it's under-predicted by our model. Here's a picture from the ECOS team that shows the most impacted area, which is the southern tip of Panjang, where we predict the high run-ups here. And the northern tip, there was an oral report of about 8 meters that matches the modeling quite well. Now, going to the far field, we have a strong directionality to the southwest, and those waves refract and affect the southwest coast of Java most significantly, but also the southern coast of Sumatra, as we shall see. It takes about half an hour for the tsunami to reach the first tide gauge here, but then there is a strong reflection, diffraction around all the bathymetric topographic features. And so we did simulations for 2 hours to be able to capture all these interactions. Looking at the tide gauges, now we have the 8 cases that were simulated compared to the pink is the data. We again have good agreement on arrival time and reasonable agreement on elevations, but one immediate thing we can observe is that even more so than in the near field run-up, there is not a lot of difference between the different volume and rheology scenarios. And this is expected as we move away from a tsunami source. The details of the source do not matter that much. And this was observed by other teams, modelers who actually took even an empirical source initially and were able to capture the far field impact quite well. These are the 2 gauges in Sumatra and make the same conclusions. Now for the run-ups and flow depths, some more details here. In the area that is most impacted, where a run-up of nearly 13 meters was measured, the flow depths at the shore, so 0 meter elevation, that doesn't quite capture that large run-up. We capture about 8 meters. But if we look more at the details now here, all the run-up points are plotted, and we can see between the old shoreline, that is all these dotted points. And here there is a very large run-up. Actually, the simulation agrees well with those very large run-ups. Another area here where large impact occurred, which is about 8 meters flow depth, but larger in run-up, was also reported by Borrero et al. And they reported 9 meters at depth 3 here, which seems to be corresponding to this darker area here in the modeling. So there is an agreement there as well. In the Panaitan Island, which is also one that is strongly impacted here, there were reports of 11 to 8 meters here. So here the scale is 8 meters, but the very dark red is much larger. So we get also a good agreement with what was observed over there. Now to the north in Sebesi, which is the island that's in between Anak and Sumatra, there is a strong impact on the southern shore, which we also predict in the 6-7 meters and is measured in here in the survey, and less on the side. So good agreement there as well. And finally in Sumatra, on the south shore of Sumatra, we get a good agreement. Here is a Wemui, which is one of the most affected areas. So to conclude, we had done initial modeling based on very indirect information, satellite observations with little knowledge of what happened underwater, but had been able to nevertheless do a good prediction of near and far field run-up tide gauge. The marine surveys confirmed the volume scenarios, but gave us more information on the failure surface, better constraint on the volume itself, but also confirmed that this was a single en masse failure, which is of course assumed in the modeling, but it was not gradual or retrogressive. And so that's an important piece of information. And also we obtained more accurate bathymetric topographic data that all this allowed doing more accurate modeling. We tested for volumes to rheologies, and everything agreed quite well with each other. We matched the new data that was measured by different teams. Now, other modeling groups considered even more complex rheologies, such as the Paris et al. And then Garfingen et al. And they concluded that the difference was not significant with the simpler rheologies that we've used, and they used different volumes and failure surfaces, but in the far field, this didn't seem to matter a lot. So one, of course, important conclusion is the study of such a catastrophic event, an island collapse, is very important because island collapses are one of the sources of potential mega tsunamis. And on a much larger scale, they could cause even larger tsunamis. And there's a recent review paper by Paris et al. Discussing that. So any kind of improvement in modeling of such events that we can derive from confronting the modeling with all the measurements such as done for ACA 2018. It's very important to help us prepare for and mitigate hazard posed by similar future events. So I thank you for your attention, and I'll be very happy to take your questions.